third lecture in Module 9 on numerical simulation of turbulent flows. So, we have already discussed the features of turbulent flows and numerical simulation procedures, and we discussed RANS turbulence models in the last lecture. And today's lecture we will discuss further on RANS turbulence models and would also discuss large eddy simulation of turbulent flows. So, let us have a brief recapitulation of lecture 2. We discussed Reynolds averaging procedure, and thereby we derived Reynolds averaged Navier-Stokes equations which contained Reynolds stress terms which was supposed to be modeled. And for that, what we need RANS turbulence models, we had discussed a brief outline of Boolean proposition and eddy viscosity models. Today we will have a brief look at, or rather slightly more detailed look at, some of the turbulence models used in Reynolds averaged Navier-Stokes simulations. So, focus for today's lecture is RANS turbulence models, and then in the second half of the lecture we would consider large eddy simulation. So, the outline of today's lecture: first we will have a look at RANS turbulence models, and then we will look at large eddy simulation, which is called LES in short. We will discuss the conceptual procedure involved in large eddy simulation. Then we would briefly discuss the spatial filtering operation of Navier-Stokes equations for incompressible flow, and then we would have a look at one or two popular subgrid scale models for large eddy simulation. Now, in RANS turbulence models we discussed two varieties. One we call eddy viscosity models, for instance a mixing length model, a Spalart-Alamaris model, standard Cape-Soylent model, Cape-Soylent RNG model, realizable Cape-Soylent model, and so on. And we also discussed briefly, noted briefly, the Reynolds stress models. Now, in this list, this mixing length model is what we call zero equation model, a Spalart-Alamaris model is one equation model, and a standard Cape-Soylent model is a two equation model. So, a standard Cape-Soylent, Cape-Soylent RNG, realizable Cape-Soylent model, or K omega model, these are all two equation models. So, we will discuss only one representative model today, that is the standard Cape-Soylent model. And Reynolds stress model, which directly works on the transport equations of Reynolds equations to obtain the Reynolds stresses directly by solving a set of 6 PDEs. So, the bold ones, that is to say mixing length model, Spalart-Alamaris model, the standard Cape-Soylent model, and Reynolds stress models were the ones which we are going to have a bit more detailed look today. So, let us have a look at the mixing length model, which is one of the oldest one, which is proposed by Prandtl, and the basic premise was based on the realization that look, let us do dimensional analysis, and through dimensional analysis we can say that look, kinematic turbulence viscosity, which has got units of meter square per second, can be expressed as a product of a velocity scale from where we get meter by second, and a length scale which will give us m into m by s, that gives us m square s, and we can multiply it by a constant. So, nu tau, which is kinematic turbulence viscosity, can be expressed in terms of a dimensionless constant and a velocity scale and a length scale. Now, this length scale would be typical of our eddy structure. Now, we can assume that velocity scale is proportional to the length scale and gradients in the velocity field. This is consistent with our earlier discussions on turbulent flows, that is to say the eddies which are there of a particular length, their velocity scales are dependent on the gradients of flow velocity. So, it is based on this particular observation which we had a look at earlier, that we can express the velocity length scale theta in terms of the length scale and the velocity gradient. Let us say here we are dealing with a planar flow, so we can say del u over del y, where u is the flow in x direction, flow velocity in x direction, and y is the length scale or the coordinate perpendicular to that. Now, we can combine these two equations, and thereby we get what is referred to as Prandtl's mixing length model. The name of Prandtl is associated because he was the one who derived it first. So, nu tau is equal to Lm square del u by del y. We have combined the length scale L and the constants in this Lm, and for different flows all that we need to know to use this particular model is to get an expression, or rather a formula which can give us the value of the mixing length Lm. Del u by del y, that would be obtained from a flow solution itself. So that's why we don't have to solve a separate equation to compute our eddy viscosity here. Now algebraic equation exists for the mixing length for simple two-dimensional flows such as pipe and channel flows. For more details, please see the book of Versteeg and Malala-Sekera. Now let's have a brief look at the advantages of this model. It's very easy to implement and requires very little computational time in addition to solving our velocity components, and it gives pretty good prediction for thin shear layers. A disadvantage is it is completely incapable of describing flows with separation or circulation, and it calculates only mean flow properties and turbulence shear stresses. So this mixing length model is used only for the simulation of thin shear layers. Okay, next category, this Parrot LMRS model. We will not have a look at the algebraic details because it is a very specialized model for aerodynamic calculations, and it is a one equation model because it solves a single conservation equation or one PDE for the turbulent viscosity, and this conservation equation, which has been derived for aerodynamic flows, it contains a convective and diffusive transport term as well as expression for production and dissipation of the turbulent kinematic viscosity. Now this was used primarily, or this was developed primarily for use in unstructured codes in aerospace industry, and it is economical and accurate for certain type of attached wall bounded flows and flows with mild separation and recirculation. Please remember the way we described earlier also that it is primarily used in aerodynamic simulations. So we are not going to have any detailed look at the equations involved. If you are interested, you can pick up any book, like for instance Versteeg and Malala-Sekera's book, or any other CFD book can give you details of this model. Next we come to the most widely used model. In fact, this K epsilon model, it is two equation model which is the workhorse for industrial CFD analysis. This is one of the most popular models, and the so called standard model, that the original model, original K epsilon model, it was proposed by Launder and Brian Spalding in 1974. It makes use of two model equations, one for turbulent kinetic energy K and one for the rate of dissipation of turbulent kinetic energy per unit mass epsilon. So that is the reason we call it as K epsilon model. So if you can solve for these K and epsilon everywhere in the flow field, so we can use this K and epsilon to obtain velocity and length scales. For instance, the velocity scale could be easily obtained by taking the square root of K. Remember, K is turbulent kinetic energy per unit mass. So that basically has got the units of velocities or dimensions of velocity square. So the square root will give us a velocity scale, and length scale is defined in terms of the turbulent kinetic energy. So that is K to the power 3 by 2 divided by epsilon. So length scale is the one which relates both the kinetic energy of turbulence to the dissipation of the turbulence kinetic energy, and we can use these two, L and theta, in our eddy viscosity model to estimate the nu tau, the turbulent kinetic kinematic viscosity, as C mu theta into L, where C mu is a dimensionless constant. Now this turbulent kinetic energy equation can be derived from our Navier-Stokes equations and invoking Reynolds averaging procedure, but the derivation of equation for epsilon, that is a bit more complicated. It involves many empirical constants here. So we will just list the two standard equations the way they are used. The first one is the equation for the kinetic energy K, or what we call transport equation for turbulent kinetic energy K. So del by del T of rho K plus del over del Xj of rho K Vj bar is equal to del by del Xj of mu T divided by sigma K del K over del Xj plus twice of mu T Sij minus rho times epsilon. So here epsilon is our dissipation term. This Sij, that is a velocity rate tensor or strain rate tensor, which can be obtained from the average velocities, that is Vj bar, and as mu T is our dynamic eddy viscosity, sigma K is a constant, Similarly, next it is a transport equation for epsilon, del by del T of rho epsilon plus del over del xj of rho epsilon Vj bar is equal to del over del xj of mu T times sigma epsilon del epsilon over del xj plus C1 epsilon by k 2 mu T Sij minus twice of C2 epsilon rho epsilon square by k. So, these two are coupled partial differential equations. In fact, they also involve the yet unknown velocity components. So, these two equations for k and epsilon, these two PDEs must be solved together with our 3 momentum equations, that is 3 equations for velocity components. And we had many empirical constants here, sigma k and sigma epsilon, C1 epsilon, C2 epsilon and C mu. So, these are adjustable constants which have been determined, or rather they have been estimated based on the curve fitting from a wide collection of experimental data on turbulent flows, and most widely used values which have been suggested based on these compilations are that C mu is taken as 0.09, sigma k is taken as 1, sigma epsilon is taken as 1.3, C1 1 epsilon is 1.44 and C2 epsilon is taken as 1.92. Now, these are adjustable constants. So, depending on the flow situations or flow type, you might choose a better value if such an indication is available in literature. Otherwise, we will just go by these most widely used values in our code for the solution of k and epsilon. And once we know k and epsilon, mu t can be evaluated using the previous formula which we have seen earlier. Now, what are advantages of this k epsilon model? It is relatively simple to implement. We have got 2 additional equations which have got similar form to that of our normal momentum equations. For instance, we had a time derivative term, a convective term, a diffusive term and something like a source term. So, the solution process would be exactly the same as the one which we are going to use to integrate our momentum equations. We have to just add up 2 additional equations, and it has been observed that k epsilon model leads to stable calculations that converge relatively easily. So, this is why excellent performance has been observed for many industrially relevant flows, and that is one of the reasons why this is one of the most widely validated and well established models, which I would say is a workhorse for industrial CFD analysis. There are some disadvantages though, which are linked basically to the way we had assumed a scalar eddy viscosity. So, it provides poor prediction for swirling and rotating flows, wherein we cannot have a scalar kinematic viscosity assumption, that does not work very well. Similarly, for flows with strong separation, axisymmetric jets and certain unconfined flows and fully developed flows in non-circular ducts. Further, this model is valid only for fully turbulent flows. If you got the low Reynolds number flows, we have got to use special versions of k epsilon model for low Reynolds number flows to cater for the flows which might be just turning into the laminar flows, that is, or transitional flows and a mix of turbulent flows. For that, we have to use low RE versions of k epsilon model. For details, please have a look at the book by Versteeg and Malala-Sekera on computational fluid dynamics. Now, there are many improved 2 equation models like k epsilon RNG model, realizable k epsilon model, k omega model and algebraic stress models. For these, and there are a few nonlinear models as well. We will not discuss in this lecture today. Please, for the details, please have a look at the book by Versteeg and Malala-Sekera. Next, let us have a brief look at Reynolds stress model, which is not based on eddy viscosity assumption. And why do we need it? There are some reasons here that this eddy viscosity model, they have significant deficiencies which are consequences of assumption of scalar eddy viscosity, and experimental measurements and direct numerical simulations indicate that in 3D turbulent flows, specifically over the complex geometries, eddy viscosity is not a simple scalar quantity. In fact, it has got directional preferences, so it becomes a tensor quantity. Hence, the use of a scalar eddy viscosity for computing Reynolds stresses is not really appropriate, and that is the reason why K epsilon model does not work very well for such situations. So, we should instead now try to compute Reynolds stresses directly using their own dynamic or transport equations. So, this particular observation is what forms the basis of Reynolds stress model, that is to say, let us derive the transport equation for Reynolds stresses and then try to solve them, but it is not as simple as it appears to be. First, it is one of the most expensive of turbulence models, and nevertheless, though we can derive transport equation for Reynolds stresses starting from Navier-Stokes equations and Reynolds averaging procedure, we will quickly realize there are more terms, which new terms appear, which need to be modeled. So, now let us define the kinematic Reynolds stress tensor capital R as Rij is equal to minus tau ij r divided by sigma, that is, it is simply equal to Vi prime Vj prime over var. So, this the average of product of fluctuating components Vi prime and Vj prime. And now transport equation for R can be derived from Navier-Stokes equations, and we can write it in following form. The first term is a time varying term, the second one is sort of a convective term for the transport of the Reynolds stresses, and on the right hand side we have got few additional terms which will their details we will have a look at in the next slide. So, that is how the equation reads like del of del T of rho Rij plus del of del xk of rho Vk Rij is equal to Pij plus Dij minus epsilon ij plus pi ij plus Eij. Now, here P is production term, D is called diffusion term, epsilon dissipation rate tensor, capital Pi is pressure restraint term, and E represents turbulent diffusion. So, Pij is given by minus sign within brackets rho Rik del Vj over del xk plus rho Rjk del Vi over del xk. So, if you look carefully, this involves only our Reynolds stress terms and Reynolds average velocity components. So, this can be easily calculated. The next our diffusion term Dij is again del over del xk of mu del Rij over del xk. So, this is again a relevant term which does not involve any further unknowns. But let us have a look at pi ij. This is an average of the fluctuations of pressure and the fluctuating strain rate, that is P prime del Vi prime over del xj plus del Vj prime over del xi time average of all of this. This is something which we do not know. So, this has to be modeled. Similarly, for epsilon ij, which is a dissipation rate tensor, is 2 mu del Vi prime over del xk into del Vj prime over del xk over var, that has also got to be computed. This also involves unknown correlations. The same holds good with Eij, which is del over del xk of rho Vi prime Vj prime Vk prime over var, which is what we call a third order moment, plus P prime Vi prime delta Ijk over var plus P prime Vj prime over var delta Ik. So, now we have introduced additional unknowns through these terms, and these ones like capital Pij, epsilon ij and Eij, they must be modeled. Okay. So, that is what is summary here, that these ones the dissipation rate tensor, pressure strain term and turbulent diffusion term, they cannot be computed exactly and hence must be modeled. There are many different models which have been proposed by different researchers which are available in literature. So, for further details on modeling of these terms, please see the first initial paper of Launder et al. In 1975 and the book by Verstegen and Malalas-Sekera, which gives you further references regarding many different proposed models for modeling these three terms. So, that is why we would put a full stop to our discussions on Reynolds stress models, with just one observation that in comparison to Eddy diffusivity model, Reynolds stress models require fairly large computational cost. That is very obvious because we need to solve 7 additional PDEs, 6 for Reynolds stresses and 1 for the dissipation term, in contrast to 2 required in K epsilon model. So, it is pretty expensive, and that is one of the reasons why these models have not been as popular in industrial CFD analysis. Next, let us move on to our large eddy simulation, which is now picking up in industrial CFD analysis. So, what is the basis? Let us have a look at what we had learned earlier in discussions on turbulent flows, and what we have observed that large scale motion, which we call large eddies, they are much more energetic than small scale eddies. And what is the consequence? It is the larger eddies which are the most effective transporters of the conserved quantities, that is, they are the ones who transport mass, momentum and energy. They are largely anisotropic, and these are the ones which we need to resolve accurately in our flow simulations. In contrast to large scale eddies, or what we simply call large eddies, the smaller eddies are much weaker and they have got very limited role to play in the transport processes of mass, momentum or energy. Furthermore, we have seen that small scale motions, they show universal behavior, they are more or less isotropic irrespective of the turbulent flow, whether turbulent flows takes place in one type of geometry or another type of geometry. So, their behavior is what we call universal irrespective of the context, Reynolds number or the geometry of the flow. So, what we can do is we can instead come up with a model for these smaller eddies. It is a lot easier to capture the effect of these small scale eddies through a model and try to resolve the large eddies accurately. So, that forms what we call the basis or basic philosophy of LES, that is to say, treat the large eddies of the flow exactly and model more universal small scale eddies through what we would call a subgrid scale model. And please remember, this large eddy simulations, they are inherently time dependent and 3-dimensional simulations, in contrast to statistically averaged or time averaged Reynolds averaged equations, where we get steady state flows simulations. Large eddy simulations are time dependent ones, and as a consequence large eddy simulations, they are more costly than RANS simulations, but they are much less costly than DNS, because in DNS we were required to resolve all these scales, small scales as well as large scales. So, our grid size and time steps were dictated by the smallest eddies, that is the ones which have size of Kolmogorov length scale. But in LES we are not going to resolve up to that scale, we will rather stop in the middle, we will just resolve the large eddies. So, we can have much larger grid size in large eddy simulation, and consequently a large eddy simulation would be much less costly than DNS by maybe few orders of magnitude, and at the same time, since it is a time dependent 3-dimensional simulation, it would be a lot more expensive than Reynolds averaged Navier-Stokes simulation for the same flow. Nevertheless, LES is preferred method for obtaining accurate time history for high Reynolds number and complex geometry flows, for which DNS is not feasible owing to astronomical computing requirements, and RANS simulations are not very accurate. We have already seen the K-Salon model is not very good for the complex geometries flow, which will involve lots of swirl and flow separations and so on. So, in such situations large eddy simulation is the one which can help us out. So, let us have a brief look at the conceptual steps in large eddy simulation. The main concept involved is that we have to somehow separate the larger scale from the smaller ones, and we would compute only the large scales of motions. So, for this purpose we have to employ a spatial filtering operation to separate the larger and smaller eddies. In case we are working in a spectral domain, then we have to come up with a spectral filter and thereby separate eddies of high wave number and small wave number. And once we have separated, the filtered or resolved scale field is the one which is simulated, that is that is the one which we would compute numerically using a suitable Navier-Stokes solver, which we already discussed earlier. So, now let us summarize the steps involved in large eddy simulation. The first step is choose an appropriate filter to decompose velocity field into some of a resolved component, that is our large eddy component, and a subgrid scale, or what we call in short SGS component. So, this SGS component is what refers to small scale eddies, and once we have chosen a filter, we would use that filter to obtain filtered Navier-Stokes equations. Now, these equations would be very similar to the original time dependent Navier-Stokes equation, except for an additional residual term which we will call the subgrid stress term arising from filtering. The word stress here is used to just maintain a uniformity with the historical perception of the fluctuations linked, which we have seen earlier in Reynolds averaged Navier-Stokes simulations. So, just keeping that terminology, we have used here the subgrid stress term, and once we have obtained the filtered Navier-Stokes equations, the next step would be that this equation will not be closed, because there would be some additional term, this residual or subgrid stress term. Now, this stress term has to be modeled, so that it is expressed in terms of our known quantities, in terms of our resolved velocity field. So, we have to come up with or use a model which we call subgrid scale model, and once that is ready, thereafter we can use our numerical simulation procedure which we have learnt earlier for Navier-Stokes equations to obtain the filtered velocity, pressure and temperature field using an appropriate Navier-Stokes solver. Now, remember here just some more comments in order that large eddy simulation, again we would like to have an accurate time history. So, very often in practice what do we do is we choose an explicit Navier-Stokes solver, because our time step is governed by the accuracy requirements. It would usually be pretty small to satisfy the stability requirements imposed by an explicit time integration schemes. And since the integration scheme is explicit, time step which is small enough to satisfy the stability requirements, we can calculate very efficiently our velocity components using this explicit time integration scheme. Now, let us have a look at the filtering operation in Navier-Stokes equation. For the time being, let us have a look at spatial filtering. The spectral filtering works in analogous fashion. Okay. So, in large eddy simulation, the spatial filtering for any transported field, the transported field could be one of the velocity components, it could be temperature and so on. So, it is defined using a filter function. So, suppose phi were our variable or flow variable. So, phi bar xt is defined as the integral of this convolution g x x prime delta, this is our filter function, multiplied by our unfiltered or the original flow variable phi x prime t dx prime. So, this integration is carried out over this spatial domain, and here our g is the filter kernel and this delta is the cutoff width. Now, we will see that we will actually do not have to perform this complicated 3-dimensional integrations, it is just a conceptual step. Okay. And there is one more comment in order, here we have used overbar, but please remember in the context of large eddy simulation, the overbar would not denote Reynolds averaging, it denotes a filtered quantity, that is to say it denotes the result of applying this filter g x x prime delta on our flow variable phi. So, I hope there is no further confusion, we are going to use this overbar to represent a filtered flow variable. Now, some of the popular filter kernels in large eddy simulation, there is one Gaussian filter, top hat or box filter, which essentially is linked to let us say our mesh size, and if you are working for a spectral simulation, that is to say our numerical simulations are being performed in a spectral domain, we can also use a spectral cutoff filter. Okay, let us see what does this filtering operation imply. It basically says that look, the eddies of size which are larger than delta, they are large eddies, and they represent a resolved or filtered field, while eddies of size smaller than delta are small eddies which are filtered out by this filter and which must be modeled. Now, this cutoff width delta can in principle have any size, but in theory or sort of in practice what do? We choose a value which is almost of the same order as that of our grid size, because a value smaller than typical mesh size in our finite element, finite volume or finite difference simulations is meaningless. So, the most common value is an averaged mesh size. For instance, this delta for a structured mesh can be obtained as delta is equal to cube root of delta x, delta y, delta z, where delta x, delta y, delta z they represent length, width and height of a typical hexahedral element. So, you can think of this delta x, delta y and delta z to be the mesh sizes in x, y and z directions on a structure grid in a finite difference method or in finite volume method, or they could be sizes of the finite element if you have used hexahedral elements in finite element simulation. Similar estimates could also be obtained for tetrahedral elements in finite element simulations and so on. So, in a nutshell, this delta represents an average value or average length linked to our finite element or finite volume cell or finite difference grid. And based on this filtering, a filtered or resolved velocity that can be expressed as Vi bar xt. Now, remember, the filtered velocity or any filtered variable for that matter, it would be a function of a spatial coordinate as well as the time. So, this is symbolically represented as g x comma x prime comma delta Vi x prime t dx prime, and application of this filtering procedure is very simple. That application of filtering operation to continuity equation for incompressible flows, that leads to a very simple form, only the time derivative term which is not there for incompressible flow. We have got only one term here, that is divergence term. So, del over del xi of rho Vi bar is equal to 0. So, if you remember, our original equation was del over del xi of rho Vi, that was our original continuity equation. The only thing which has changed for the filtered equation is we have just replaced Vi by the filtered velocity Vi bar. Similarly, let us now apply the filtering process to our momentum equation. So, we can substitute each term or each variable term in our momentum equation by the filtered counterpart, and that would give us the filter momentum equation, for instance. And the second term is the convective term, the third term is the pressure gradient, and the last one is our stress term. Okay. So, if we remember, our original equation was simply del over del t of rho Vi plus del over del x of rho Vi Vj is equal to minus del p over del xi plus del tau ij over del xj. I have ignored the source term because that would remain unchanged from the filtering operations. If it is required, we can always incorporate here. In majority of the flows, that source term can be absorbed in a pressure term. So, that is why we have not put here explicitly. So, now remember what we have done. What is the net effect of filtering operation? Vi has been replaced by Vi bar in the first term. So, our temporal term becomes del over del t of rho Vi bar. Similarly, in the second term, the convective term Vi Vj bar, this product is replaced by Vi Vj over bar. So, the convective term becomes del over del xj of rho Vi Vj over bar is equal to minus del p bar over del xi. We have just replaced p by the filtered pressure field plus del over del xj of tau ij bar. Now, tau has been replaced by the filtered counterpart. So, this tau ij is defined as mu times del Vi bar over del xj plus del Vj bar over del xi. That is to say, all that we have done is, in the standard definition of tau ij, we have just replaced Vi and Vj by Vi bar and Vj bar, that is the filtered velocity components. So, this equation has got a form very similar to our original Navier-Stokes equation, except for this convective term, because in convective term now we have got here a cross correlation term Vi Vj over bar. So, we have now somehow got to change this term, and for that purpose what do we do? To represent the convective term in terms of the resolved velocity field, let us introduce subgrid stress term, and it is also referred to as subgrid scale Reynolds stress term, in analogy with our Reynolds stress models, or what we call Reynolds average Navier-Stokes equations, where we called a term involving velocity fluctuations as Reynolds stress term. In earliest literature, some people prefer to use the term subgrid scale Reynolds stress term, and this particular tensor is defined as tau ij. Let us use the superscript s to differentiate it from our Reynolds stress in RANS models. So, tau ij superscript s is equal to minus rho within brackets Vi Vj over bar, that is the filtered value of this product of Vi and Vj minus Vi over bar into Vj over bar, and introduction of this would be now this minus this rho times Vi over bar Vj over bar, that can be transferred to the left hand side, and the remaining terms could be absorbed, put in the right hand side to get a form which is now analogous to our original Navier-Stokes equation. So now this subgrid stress, what does it represent? It represents the large scale momentum flux which is caused by small or unresolved scales, and since it involves a term which we cannot compute explicitly using our filtered velocity value, that is Vi bar and Vj bar, this term Vi Vj over bar cannot be computed in terms of Vi bar and Vj bar explicitly. So this whole term, this tau ij s, it has to be modeled to ensure the closure of filtered Navier-Stokes equation, and this modeling is referred to as subgrid scale modeling. Now let us substitute this tau ij s in our filtered equation and rearrange the terms. Del rho Vi bar over del t plus the next one is convective transport term, del over del xj of rho Vi bar Vj bar is equal to minus del p bar over del xi. So this represents a pressure gradient term plus del over del xj of tau ij bar plus tau ij s. Now tau ij bar, that is represented in or expressible in terms of velocity strain rate tensor, and this tau ij s, that is something which we have to obtain using our subgrid scale model. But if you look at the form, this form is exactly same as our original Navier-Stokes equation, except for this additional term on the right hand side which we would compute somehow and incorporate. So any code which we have written to solve our Navier-Stokes equation, so any standard Navier-Stokes solver can straightway be used for large eddy simulation. We do not have to solve for separate partial differential equation in this case the way we did in the case of the RANS models, typically let us say our Cape-Solin model or Reynolds stress model, where we had to solve for additional partial differential equations. Here we do not require that in our large eddy simulation. Now we have to find out the expression for this subgrid stress term. So there are many subgrid scale models have been proposed in the literature, starting from this Smogensky model in 1963. Smogensky was the first person to come with the large eddy simulation for atmospheric boundary layer, and there he proposed a very simple model in analogy with the Bogin eddy viscosity proposition, and there are many improvements proposed over Smogensky model. So one is called scale similarity model, which was proposed by Bodina et al. In 1980. Then dynamic subgrid scale model. So I have just mentioned only the most popular ones of them here. There is feverish research going on to come up with Bader and Badel subgrid models based on the DNS data and very accurate experimental results. So for more details, please see the book on computational fluid dynamics by Verstegen and Malal-Sekra, and for even more details you can see the book on turbulence by Legier in 2008. In fact, this one full book by Legier which is devoted to large eddy simulation. So that will contain the models developed up to year 2004, and still research work continues to obtain more and more improved large eddy simulation models. Now let us have a look at our Smogensky model. So Smogensky model is an eddy viscosity model. That is how it was, its inspiration came from there, from the eddy viscosity model which we have discussed earlier in the context of Reynolds stresses or Reynolds averaging process. So in this case the local subgrid stress is taken to be proportional to the local rate of strain of the resolved flow. That is to say, this tau ij s, this is our subgrid stress tensor, this is equal to 2 mu t. I have purposely used small t here to say that this mu subscript small t is our subgrid scale eddy viscosity. So tau ij s is twice of mu T Sij bar, which Sij bar is our strain rate tensor based on resolved velocity field, that is Sij bar is half of del Vi bar over del Xj plus del Vj bar over del Xi, okay, plus next term is 1 by 3 tau kks delta Ij. So this is Smorgasky model. Now here, to use this model we need an estimate. The modeling comes from how do we obtain an estimate of mu t. So that is the modeling part. Okay, so what Smorgasky proposed is this SGS eddy viscosity, it is proportional to the subgrid length scale delta and a characteristic turbulent velocity. Now a turbulent velocity can be obtained by the product of the length scale delta and a scalar product which we can obtain from our strain rate tensor. So let us call it as magnitude of S. So thus we can write mu t as rho times Cs square delta S square S bar, where this S bar magnitude is given as square root of Sij over bar Sij over bar. So this Sij over bar into Sij over bar, this is a doubly contracted tensor product of our strain rate tensor. So that will give us a scalar quantity, take the square root of that, that is what this particular symbol S bar modulus represents. So this S bar can be easily evaluated from our resolved velocity field, we can easily calculate that. Delta is known to us, rho is of course known to us, then Cs is a constant value which we call a model parameter. Now this Cs is not a universal constant, it depends on the type of flow and different values have been suggested for different types of flows. For instance, for isotropic turbulence Cs was taken as approximately 0.2. For channel flows a lower value of Cs is equal to 0.06 or some people use 0.1, that is usually recommended. Similarly for wall bounded flows, if you use this, even Cs is equal to 0.06 or 0.1 is too large a value. So modification was suggested that for regions close to the wall this value is reduced further using one drift damping. This was proposed by von Drist and that is why it is called as von Drist damping, that is to say reduce the value of this constant or this dimensionless number in evaluation of our eddy viscosity further. So Cs close to the wall would be expressed as Cs0, where Cs0 could be over 0.1 or 0.06 within brackets 1 minus exponential of minus n plus divided by a plus bracket close whole square, where this n plus represents the non-dimensional distance in wall units, that is n plus is equal to n u tau divided by nu is your kinematic viscosity, u tau is what we call wall shear velocity which is given in terms of shear stress of the wall, that is u tau is equal to square root of tau w divided by rho, and a plus is a constant whose value is approximately taken as 25. So this is our von Drist damping, and large eddy simulation based on a Smorgasky model normally makes use of the von Drist damping close to the wall for wall bounded flows. Next let us have a very brief look at scale similarity model. The basic reason which Bardina et al. Argued was that important interactions between resolved and unresolved scales, they would involve what? They would involve the smallest resolved eddies and the largest eddies of unresolved scales. So their interaction is the one which is most important, and maybe your isotropic model may not be able to incorporate that interaction. So what we should do is, there is a similarity which exists between the smallest resolved scale and still smaller unresolved scales. So if we can use a double filtering, that can help us out. So that is based on this argument Bardina et al. Gave its scale similarity model. They said tau ij s is equal to minus rho Vi bar Vj bar minus Vi double over bar into Vj double over bar, where double over bar indicates a quantity that has been filtered twice, that is we have applied the filtering twice to determine the values of these velocity components. Now, there were some problems with this model, that though it correlates very well with actual SGS Reynolds stress, but it hardly dissipates any energy. So, turbulent flow simulations usually blow up if you use this model. Hence, to stabilize the computations, additional damping is introduced in the form of Smogensky model. So, we add that additional damping, and that leads us to what we call a mixed model. The first part is our scale similarity model, and the second one is our similar to Smogensky model. So, this mixed model is tau ij s is equal to minus rho Vi over bar Vj over bar minus Vi double over bar Vj double over bar plus 2 rho Cs square delta S square modulus of S bar into S bar Ij. And this scale similarity model with this enhanced damping, it works pretty well, and it gives us what we call a stable large eddy simulation model. There are many more models which are available, but we do not have time to discuss them in detail in this course. So, I would refer you to look at some of these books. For instance, for turbulent flows, for the most recent turbulence models, including the more advanced large eddy simulation model, please have a look at the book by Lec-03 et al., Turbulence 4th edition. This book was published in 2008 by Springer. Similarly, for details of turbulent flows, including different scales and turbulence models, you can have a look at turbulent flows book by Pope et al. For numerical simulation related thing, Chung's book also gives us quite some details. Similarly, you can have a look at the book by Fertziger et al. On computational method for fluid dynamics, and this Versteeg and Malala-Sekharaj book on finite volume method, that is Introduction to Computational Fluid Dynamics, the finite volume method. This has got one full chapter on numerical simulation of turbulent flow, that is on turbulence modeling. It also gives you in bit more detail many RANS models and some of the LES models, and few indications of which model to use in what situation, what are the advantages and disadvantages of different models, and which is supposed to be used in certain flow situations. So, please have a look at that chapter in this book. Next references on what we saw today related to large eddy simulation. We refer this scale similarity model of Bardina et al., this Bardina, Fertziger and Reynolds, which was derived in 1980, called improved subgrid scale model for large eddy simulation. Similarly, we briefly mentioned a dynamic model. So, this dynamic model, it computes this CS coefficient dynamically depending on the local situation. So, it is called dynamic subgrid scale eddy viscosity model. And this Smogensky model, which was the original or what we call initial large eddy simulation model. As far as this particular course is concerned, we would stop here. We are not going to discuss any more turbulent models in details. So, for further details, as I mentioned, please have a look at these two books, the book by Lec-03 and book by Versteeg and Malala-Sekharaj, which will give you a lot more information regarding the turbulent flow simulations. So, for this module we stop here. In the next module we will consider a few practical aspects of CFD linked with grid generation and what else we need to do to validate our CFD simulations.